Hello to everyone, and welcome to this webinar in which we are going to review, to speak about the DC-AC radio and how to choose the right size of your solar inverter. First of all, I would like to thank you all for joining this webinar. I hope that you will find it useful and that you will find some things interesting for you in this webinar. And we are going to wait a couple of minutes just to have everybody in the call, and after that we will start with the presentation. Okay, so after these 2 minutes of wait, I think that we can start with the webinar. Again, thank you all for joining. I hope that you find this webinar interesting. And well, during today's session, we are going to speak about the DC-AC radio and how to choose the right size of the solar inverter. We will see how can we optimize this value and this parameter that is very important for when designing a PV plant. And to do so, the agenda for today is going to be the one that we can see in this slide. First, we will review the definition of the DC-AC radio, why we are defining this radio when designing a PV plant, and what implications we may have within the plan when defining this DC-AC radio, what things can we optimize, and what dependencies we have within the plan regarding to this DC-AC radio. Second, we will go through some use cases that I have, some case study I have prepared within PV design, in which we will iterate through some different projects, and we will see in different circumstances how can we optimize the DC-AC radio. And finally, we will have some space, around 20 minutes, for questions and answers, in which I will try to answer all the questions that you may have had during the presentation. And if you have any question at any moment of the presentation, please, you can directly write it in the questions box, and we will go through all of them at the end of the presentation. About me, well, my name is Álvaro Pajares. I've been working for RatedPower for more than 2.5 years now. I started working for the customer success team, RatedPower. And after 1 year more or less, I started working for the product team, where I'm working right now. And here what I'm working at is as a project engineer and software developer of some of the new features that come with PV design. Before kicking off with the webinar, I would like to comment that we have just announced Pulse, which is the Global Renewables and Energy Transition event that will be hosted by RatedPower and Enverus. And in this event, you will be able to join hundreds of pros like you in a unique 2-day event on April the 19th and the 20th in Madrid. And if you want to have more information and also grab your early bird tickets, where you will find some discounts until the end of February, you can go to the web that we can see here, ratedpower.com/pulse, and you will find more information about the event per se. And if you have any questions also, you can write them in the questions box. So going directly to the presentation per se, first, as I mentioned, we will review the definition of the DC-AC radio. As we all know, when producing energy in a photovoltaic plant, first, let's say that the sun radiation is transformed into DC power by the modules that we are installing, and later with the inverters we will transform that DC power into AC power. This DC-AC radio what it is that basically the ratio between the rated DC power of the modules installed, which will be the power that is given for the modules in the datasheet or in the nameplate, and the rated AC power of the inverters that are installed. Why this DC-AC ratio is so important when designing PV plants? Well, the most important thing is that when rating the DC power of the modules, this DC power is given at the standard conditions, which are the cell temperature of 25 degrees Celsius and a solar irradiance of 1,000 watts per square meters. That will mean that the ambient temperature could be around 0 degrees Celsius, and so these conditions are like not normally met during operation of these modules. So that's why we will try to find what's the best DC-AC ratio that fits better within our plant, so that we are oversizing a bit the inverter, knowing that at some point we may incur into some losses due to the power limit of the inverter, but we are not like giving too much space for inverters and in many times not using the power that the inverter has. Here I have included some of the dependencies that this DC-AC ratio has. First of all, and one of the most important ones, is that this DC-AC ratio will be completely site dependent, depending on the location in which we are designing the PV plant. We will have some characteristics or others. And for example, I have added a couple of meteorological data from the south of Spain and from Netherlands, and we can see how the meteorological conditions are completely different. In the south of Spain, we will have more irradiance and more temperature, while in Netherlands we will have less irradiance and less temperature. So we could see that here it looks like there will be many differences when in the operation of the modules in both locations, and the DC-AC ratio in both locations could be completely different. Also, other characteristics such as the topography of the terrain could affect this DC-AC ratio. If we have a slope that is facing the north, maybe we could have a DC-AC ratio completely different to a slope facing the south, or other different aspects. Then another dependency that I have included is the equipment dependent. The DC-AC ratio depends a lot on the equipment that we are defining. For example, we are not going to have the same DC-AC ratio we are designing with a monofacial or a bifacial module. Bifacial modules, the rated DC power that they have do not consider the back phase production that we are getting. So we may think that with bifacial modules, the DC-AC ratio objective may be a bit lower. Also, for some inverters, we are going to have like a restriction on the number of physical inputs that we can put into that inverter, and that way we will have a limitation somehow of the DC-AC ratio that inverter could have, as we will have a limited number of inputs within that inverter. And finally, I wanted to also include the dependency within the design criteria that the person in charge of the design has decided to use. And here I wanted to mention, for example, that it's very dependent on the distances that we are leaving between the structures, the GCR that we are using, as this will imply more or less shades. For example, depending on the shades, we may have one desired DC-AC ratio or another, and it's also very important to consider this design criteria when defining the optimal DC-AC ratio for one specific project. So going to the inverter, I wanted to add these graphs where we can see the operation window of one inverter, and how the fact that we put more power in the DC input of the inverter may incur into some losses at the inverter, as the inverter is not able to transform all of that power into AC power. Also, I wanted to add one image that is related to the power factor that the inverter has, as we will need to consider also the power factor that the inverter will have when defining the DC-AC ratio. Why do we have to consider it? Well, from the DC field, we will have a certain active power reaching. The inverter will be able to convert that power into active AC power, but also can give a plus for the reactive power. We must consider that amount of active and reactive power is not exceeding the maximum apparent power that the inverter may have. And if we don't consider that, we may also be incurring into some losses due to the power factor that we have defined. So with that being said, as a summary of the definition of the DC-AC ratio, we have a kind of a trade-off here, because we know that if we increase the DC-AC ratio of the plant, it will increase the losses at the inverter, because we will have more situations in which at the input of the inverter, we will have more power reaching the inverter, and we will incur into some losses. However, we will have also the fact that if we increase the value of the DC-AC ratio, we will decrease the cost that is associated to the AC equipment. So that's why we will try to oversize as much as possible the inverter, so that we reduce the cost of the PV plant. So with that being said, now I would like to go through some of the use cases that I have prepared. We are going to review some of these dependencies that I have commented, and try to find what's the best DC-AC ratio in different circumstances. Before going through these use cases, I wanted to present how do we calculate and what options do we have in PV design regarding the DC-AC ratio. For us, the DC-AC ratio is defined as the rated DC power of the modules and the active AC power of the inverters, so that there we can consider also the power factor at the inverter's output and reduce the losses according to this power factor definition. And then also in RatedPower, we are going to have information about the maximum number of strings that could reach one inverter. This way, one user could go to this box where they are defining the DC-AC ratio, and could directly see what's going to be the maximum number of strings that can reach one inverter, and check that this value is not exceeding the one given by the manufacturer. Also from this box, we can see that it's possible to define not only a global DC-AC ratio, but also some limits if we want to install the maximum peak power in the plant. And this way, the user will be able to define in what range they want the inverter to be working. So now the first case study that I wanted to propose is one case study where we are going to review basically the first dependency that I was mentioning, the site dependency, and we are going to compare one site that is going to be located in the south of Spain with another that is located in the Netherlands, with a PV module of 500 watts, a monofacial module, a string inverter of 250 kVA. We are going to just evaluate one inverter, and then we will try to extrapolate for the whole plant, and with one V tracker with just one string installed. The objective of this case study is going to be to find what's the best DC-AC ratio to minimize the LCOE of both specific projects, and then also compare that best DC-AC ratio that has been obtained with a reference case where the ratio is 1.2, which is a value commonly used in the industry. So we can check how do we deviate on regards to the LCOE when using one ratio or another. To do this case study, we are going to use the tools of the batch design and the comparison tool. And before showing the results, I would like to explain you how did what's the process that I followed in PV design before going with the results. As I mentioned, as equipment, I have defined a module which is monofacial with 500 watts. Then the inverter will be 250 kVA, a string inverter. The structure is structure 1V tracker. And then in the layout, I have defined the specific capacity by just defining one inverter in the PV plant. Then if I go to the cost, this is the template that I have used for to calculate the LCOE and the capex of the plant. This template is a public template that is given in PV design by Irina, specific for each country in which we are working. But I have also modified the entry which fits the inverter, so that we consider as the unit of reference the rated power, see how much affect really actually the rated power in the LCOE and in the capex of the plant. After that, I will go to generate multiple designs. I have set a DC-AC ratio step value of 0.05. And with that, once we click on generate designs, 10 designs will be running in parallel with different DC-AC radios. And in less than 1 minute, we could click them and go to the comparison tool, where we will see the filters that we have selected, the variables that we want to compare. And by sorting them by the LCOE, we will see what's the best option for this specific project in which we are working. In this case, for the south of Spain, in Cádiz, we can see that the best solution was a solution that is actually close to the reference value of 1.2, which was 1.18. And then the second best option is 1.24. So what I did afterwards to check what will be the LCOE obtained after extrapolating with these two radios will be to select maximum capacity and say that I want to install the maximum peak power. I will define as the lower radio the one that I have also as desired, and then as the upper the one that the second one that was the best solution for this specific project. And also I checked here that the maximum number of strings per inverter was below the maximum accepted by the manufacturer for this specific inverter, which was 24. And then we will get like the whole plant with inverters all working within this range that we have defined. And the ideal, the objective that the algorithm is following is that it will try to install as many inverters with this radio as possible, but if it's not possible, it will go for this radio. After that, we will generate the design and we will get like the optimal solution for this specific project, which was in fact this solution that we can see here. So the radio will be 1.19 with all the inverters working within the limits that we have set. So going back to the presentation, if we see the results that we obtained in the south of Spain, as I mentioned, the DC-DC ratio that was optimal was the value of 1.18. But if we go to the Netherlands, we will see how it's increased. And in this case, the ideal DC-AC ratio will be 1.29, and the second one will be 1.35. So we can see how the differences are huge, are very high. It's very dependent on the site, the optimal DC-AC ratio. And here we can see what the gain in the LCOE that we got with the optimal solution when comparing it to the default one. In the case of Spain, it wasn't that big because the optimal ratio was pretty close to 1.2. But we can see how in the Netherlands we are gaining an important value here with the LCOE when defining the optimal DC-AC radio. Then going to the second case study, I did a evaluation which is pretty similar to the first one, but now instead of reviewing the site dependency that I was mentioning here, I wanted to review the equipment dependency and see how dependent the DC-AC radio is with the equipment that we are selecting. And I define the same parameters as before, but now I wanted to compare what DC-AC ratio we could get if we were designing with a monofacial module and with a bifacial module. These modules will be of the same power and with the same size, but the technology for one module will be monofacial and for the other one will be bifacial. Again, I have followed the same procedure that I mentioned before, doing the batch design and also using the comparison tool within PV Design. And well, the first result will be the same as before, as I didn't modify anything from the project that I mentioned before. But we can see how for bifacial modules, the optimal DC-AC ratio will be a bit lower than the one for monofacial. And this is due to the bifacial gain that I was mentioning, which is not considered in the rated DC power for this bifacial module. And we can see how the gain in the LCOE is a bit more than for the monofacial modules. Even if in this case we think that the values are pretty close, I know that for the big plan, and if you compare that for the whole plan with 100 megawatts, it will be like an important gain when designing the PV plan. Then the last case study that I wanted to test will be related to the design criteria that we have defined and how this can affect the DC-AC ratio. And now I'm gonna go back to the Netherlands with the monofacial module, but I'm going to compare with a fixed structure, a GCR of 25% with a GCR of 60%. We will be like two completely different values so that we can evaluate how also the design criteria is affecting this DC-AC ratio and how the shades can be very important when defining the optimal DC-AC ratio in the plan. When we go to this specific case study, we will see that with a GCR of 25%, the optimal DC-AC ratio will be 1.24, which compared with the case of case study 1 in Netherlands, it's a bit lower due to the fact that the GCR is very low and no too many shades appear in this design. But if we go with a higher GCR, we can see how the DC-AC ratio is 1.4, the optimal one, and it's the deviation compared to the DC-AC ratio of 1.2 is very high. If we review the results between the optimal DC-AC ratio and the default DC-AC ratio, we can see how for the 60% of GCR, the gain is huge, is very big. And here the reason why the optimal DC-AC ratio is so high is the fact that there are many losses due to near shading in this specific design. And so we are like losing the power before reaching the inverter, and we can even oversize more the inverter because the power was being lost before. If I go to this specific design, oh wait, it's in Netherlands. Okay, we will see that the losses due to near shading were around 15%, so that's why the DC-AC ratio that we would like to have in the plant will be 1.4 instead of the 1.24 that we were getting for the same specific site, but completely different design criteria that was being chosen. So that was mainly what I wanted to present you. Now we have time for the questions and answers. Again, if you have more questions, you can write them in the questions box. And yeah, thank you again for being here with us. And I will go ahead and answer the questions that you may have. At which temperature do we usually consider the AC power when calculating the DC-AC ratio? That's a very good question. It will depend on the person that is designing And I guess that on the country in which we are designing and the conditions that you will have here, the value that we are taking in RatedPower in PV design is going to be by default the maximum power that the inverter has, but also the user can modify this value so that if they know that it's the maximum one, in this case it's at lower temperature. If they know that the inverter is going to work at higher temperature, they can also modify the value from the box, and the ratio will be considering the value defined here. Then the following one will be, is the rated AC power of the inverter before or after the conversion losses? The inverter AC power taken into account is the one before the conversion losses, like directly the value that is given from the manufacturer as the maximum power, also converted into active power, of course, considering the grid requirements that the user have defined here. Depending on this value, we will calculate what's the resulting power factor at the inverter's output, and this will be applied to the DC ratio so that we consider these requirements when sizing the PV plant and when giving the amount of inverters installed. Which ratios do you see in practice in Central Europe, Germany, Netherlands, UK? Well, here I can say that in these locations it's higher normally than in Spain if we maintain like the design criteria and the equipment that we are using. But as we have seen, I will say that it's not only dependent on the site, but we have many variables playing around here. And depending absolutely on the inputs that we are defining, equipment, design criteria, we will get one DC-AC radio or another. So depending on the design per se, we will get one DC-AC radio or another. But I will say that in these countries, it will be like if we are comparing the site, just the site, for example, in this case, when comparing the south of Spain with Netherlands, so it's like 1 point above the value that we define in Spain, so will be like about that range. Some inverter manufacturers allow radios of up to 2.0. Will this be reflected in your software? So here what we will have in the software, the value that we are taking as the maximum apparent power that the inverter can have is the value that we get here from the manufacturer. And the ratios, the maximum ratio that we accept in the software will be 5, if I'm correct. Exactly, will be 5. We could define a DC-AC radio of 2 here. This will be the relation between the DC power and the active AC power of the inverter. And if we are incurring into some losses so that we are putting too much DC power within one inverter, that will be reflected in the losses of the results of the designs. So if I go to any of these designs, we will see how much power we are losing due to the inverter power limit, also due to the inverter power factor, as in this case, we didn't add any restriction due to the reactive power requirements. It will be 0, but both cases will be considered. And so if we are above the inverter limit that we have defined in the equipment tab or the one given by the manufacturer, we will be having additional losses, but the ratio that we can define here within the software is up to 5. Also here, I must say that, for example, if we have that situation with a ratio of 5.0 0, and we have more than one strings per structure. Let me change the structure. For example, 2. What we can do is that we will see here that, well, this is going to be, if we see that the maximum number of strings that can reach one inverter is too high, what we can do also is from the electrical tab, define a harness solution. What this harness solution will do is that it will collect strings within one structure, and so in this case, for example, if we select 2 strings per harness, instead of having 38 inputs going to the inverter, we will have 19, and then we will be within the limits of the inverter. Okay, you have optimized towards the LCOE. What else can you optimize towards to? So here it's up to the user mainly from the comparison tool that we have now. If I select, for example, these 2 designs, in the comparison tool, right now from financial parameters that we can define will be the LCOE and the specific price and the total price and the capex of the plant, and these will be the ones that the user can compare regarding the financial analysis, but also, for example, if they want to just check what's the best solution in terms of energy production, they can also sort the designs by energy or also by a specific production, by peak power. It will depend on the variable that the user want to compare. Which modeling software did you use to simulate the case study? The software that we used was PVDesign, which is the software that we developed at RatedPower. And all the case studies were following this, using this software. And this way we could like evaluate the financial analysis, the energy production, also the layout, and compare the differences between the different parcels or areas. And it was PVDesign, the one that we have been using. What will be the biggest cost savings factors on AC side when raising the DC issue area? Well, I will say, well, on the AC side, first, the fact that you are going to install less inverters, that's a gain for sure. But not only that, well, inverters, power transformers, power stations, the cables will be, the number of cables, of AC cables that we are going to install is less, even the number of MV cables. So from let's say that if the PV plant goes from modules to inverters to power stations, substation, up to the inverter, the cost will be similar, but then from the inverter, we will be reducing like the electrical cost, the installation cost, and the inverters per se, that we will be like investing less money on the inverters. What is ideal like DC radio for an stable grid requiring higher reactive power? Well, here it will depend on how we are defining the DC radio. For example, in this case, what we consider as the DC radio, as I mentioned, is the relation between the DC power, the DC active power, and the AC active power. So in that case, if we have like very high grid requirements in terms of energy in reactive power, if I put, for example, 0.8, as we are doing the calculation to the inverter's output, and then the ratio that we are calculating is with that active power, what will happen is that, for example, in this case, we can see that the active power of the plant was 19.5. And now it's the same, but we have like a different DC ratio. Wait 1 second. The DC ratio is gonna be like related to the inverter. The active power is the same, but the amount of inverters that we will be installing will be increased, so that the inverters that we are installing could like take into account the reactive requirements that the grid has, and this way we wouldn't need like any extra equipment to face the reactive requirements. So even if the relation between the apparent power and the DC power could be modified, the DC generator that we define here could be similar, and the losses that are being incurred due to the power factor limits will be the same, because we are considering the active power of the inverters. Okay, does the calculated cost include only the components or the total cost of the installation? So here, in the case that I was using, what we have done is that we have checked from the IRENA cost. We have checked what are the entries that they consider from when defining the cost of a PV plant. We have separated all of them and added all of them here, but having as the unit the main peak power of each one of these entries. But the good thing is that also here we could create new templates and create different templates, also modify the reference unit that we want to consider. If we want to go deeper on the financial analysis that we are doing, and for example, we want to say, okay, I know that each module is going to cost me a certain amount. We can do that, also save that as a new template and consider that for the new financial analysis. And that way we will be going deeper into each specific element that the software is considering for the layout, all the equipment that we are including, the racking and mounting. We have many units that we can consider, and this way, depending on what's the needs of the users, they can define them here, create their own templates, and check with that templates what's gonna be the LCOE and the capex of the plant. Okay, I have seen. Can you explain again on why the DC has to be oversized? Isn't it that oversized DC plants may have higher clipping losses than plants with a slightly higher or same DC value? Okay, exactly. That's the thing. But let me go back and compare, for example, this design in which the DC ratio was very high. As you were mentioning, the inverter power limit, we are having a lot of losses here. So we are losing a 7% due to the inverter power limit. But if I go to the first design in which the ratio was 1, here the energy produced will be higher, as the inverter here we don't have any loss due to the inverter power limit. But the thing is that if we think that a good DC ratio will be 1, we expect that all the modules will be working at the standard conditions, and that way we will be sizing the inverters. As that's not the operational real conditions, if we keep increasing a little bit the DC ratio, not going that high, but increasing it a bit, in this case, well, it's the same, sorry. In this case, 1.08. We can see that still we don't have any loss due to the power limit, even if we are oversizing the inverter with the DC power. If I keep increasing the DC ratio with 1.13, here we have a little bit of losses at the inverter, 0.04, but we can think that maybe we prefer to have these losses, but reduce the cost in the AC side, and that way we will have a better LCOE. And that's what happens. Actually, the best LCOE was reached with the 1.18, where we have a 0.36% of losses due to the power limit of the inverter, but still we will be like reducing in a higher way the cost due to the AC side of the plant. And if we increase that DC radio, sorry, here is where we will find that these losses are too much when comparing to the gain that we have in the price, that in the cost that we are reducing from the AC side. So we will prefer 1.18 due to the fact that the energy here is like playing also an important role, and we will prefer that save in energy, that increase in energy rather than that save in the cost of the inverter. That's why we would like to oversize a little bit the inverter up to the point in which the losses are getting too high, and that the increase in the decrease in the cost of the inverter is not good enough when compared to the decrease in energy production. Are you considering the shading from the windmills which are in the vicinity? No, currently the algorithm that runs the energy model in PV design is a 2D calculation. So the near shadings are not yet like implemented that way. What will be considered is the shades that structures do with themselves. So what are the shades that other structures are giving to structures? And yeah, hopefully in the near future, we are also working on a 3D energy tool. We are starting to work on that. And hopefully in the near future, we will have also the 3D calculation that will consider also the topography and the 3D conditions of the site. Well, what will be an acceptable overload loss of this AC radio when simulating PV design? Well, as I mentioned, it will depend a lot on the site, on the conditions per se. Each site has its own meteorological data, conditions, topographical data, distances, and for each one of those, we will have to do like a deep evaluation on what's the best DC-AC radio. Normally considered DC-AC radio in the industry is 1.2, but as we have seen, if we go further with the evaluation, we can find some cases in which the decrease in the LCOE is very high if we go deeper with evaluation, and we will be saving like a lot of money. Have you validated your model versus PVCs and or versus real power plants? Yes, we have validated the model with PVCs. We have a Black and Beach report which validates the model that is running PV design compared to PVCs. Yeah, you can find it on our website, and also after the meeting we can send it to you so that you can take a look. For bifacial modules, are you using the module nameplate output, or are you adding any percentage for bifacial gain? Currently, we are directly taking the nameplate output, and that's why, for example, in this case, the DC-AC radio will be lower. Also, we didn't add any bifaciality factor because it will depend also the amount of energy that will come from the bifacial side or from the back face, sorry, will depend a lot on the conditions in which we are designing on the PV plant per se, and that's why we are taking directly the DC power nameplate. I see that there are many other questions that we are pending to answer, so that we don't have like more time to review them, but we will take them and we'll reach you by email, and we will answer all of them, so that I hope that all the questions that you have may be answered. And yeah, I think that was it about the presentation from the webinar. I hope you found it useful, and it was a nice topic to speak about, and that you could learn something from today's topic. And well, that's all from my side. Very Thank you very much for your attendance, and hope to see you soon.